Okay, we didn't jot it down, but tsunamis, they're big, right? They travel way faster and can travel way faster than I would ever assume or have thought of, up to 600 kilometers per hour, which that's like a jet, 400 miles per hour. That's crazy fast. Okay, beyond that, they get gigantic, and they can have wavelengths greater than 200 kilometers, which is insane because you get a huge amount of water traveling. Cool. All right, last couple. We get small differences in density. Water changes as you get deeper, right, Huggins?
Absolutely.
What changes about it?
The length of your wave.
Okay, so that's right. As you get deeper in water, the temperature and the salinity happens to change, and it varies by depth. So we talked about, at least briefly, but we'll make sure we get them. We have this idea of internal waves. Now, I'm pretty confident that if I said right now, in your mind's eye, imagine a wave in the ocean. If you can visualize pictures in your brain, which not everybody can, which is just kind of interesting on its own, you probably all just envisioned a wave traveling on the surface of the ocean. That's natural. Now, remember, where the surface happens is where we get some fluid called water that's super dense compared to the fluid that it's meeting called air. Okay, air is a fluid. It's not synonymous with liquid. They're both just different densities. Now, internal waves, we're just going to put a small little definition. Under the surface, if we start going deep in our ocean, couple things wind up happening. We know that it starts to get colder a little bit as you go deeper, but then as you get colder and colder, remember water does that wonky thing where until 4 degrees it sinks, and then between 4 and 0 and even colder than that, it starts to rise again. Under the surface, we get different densities of water. We get varying densities. I'm going to write that one out. Okay. Varying densities. Now, I alluded to like several of them a moment ago. What might be responsible for different densities if I go 100 feet down? Pressure differences definitely exist. Other things? If you're in the Bahamas and you're like snorkeling, you're probably pretty comfortable on top, right? If you go 100 feet down, would you still be comfortable? The pressure is going to be huge, but if you pop your ears and make sure you adjust for that on the way down, you'd be okay. What else would be uncomfortable about being that deep? It gets a little bit darker, so it'll be hard to see. It's also way cold. Like immediately it gets cold. If you ever swam in the ocean, like you don't have to go very deep for that to happen. Now, we get varying densities, and this can be for a variety of things. If there's runoff that flows into the ocean and you get salt water and fresh water, they're different densities. Which one is more dense? Salt water is a bit more dense. There's more stuff in it, so it has more density, more mass per volume. Okay, as we look at this, where these different densities of water meet, if it's distinct enough, where these meet, it acts essentially the same as when we have the air and the water meeting up top. That different density, we can see waves traveling through it. The same thing happens in our sea. Now, we're going to refer to this, where the different densities meet, the pycnocline, P-Y-C-N-O, pycnocline, is where these things meet. Now, the thermocline also exists, and I think we saw that when we were talking about the density at temperatures. The thermocline is where we see a distinct change in density due to temperature of the water. Now, when this happens, just like on the surface, if we have air and water at different densities, you can see a wave propagate through it. Like we can see it visibly with our eyes. Okay, down underwater though, if you have less dense water and dense water, it's harder to see because water looks like water, but there are waves that also travel underneath the water that we just can't see. Now, that's all fine and dandy. They vary a lot. For these, the period of these, which means from crest to crest, how long does it take, or what's the distance? Time is what I'm thinking. The periods of these underground waves, they go from seconds, which is like more akin to what's on the surface, up to hours. It can take 4 hours or more for crest to hit the crest once you're down to the picnic line. It can happen way, like, really slow. Now, beyond that, that's fine to mention. Why on earth would this apply to a oceans or marine science point of view, whether we're talking about physical oceanography or the biology of stuff in the ocean, what would this possibly do with life in mind? We'll focus on the life side. Love the awkwardness. Here's my challenge, rather than just asking everybody, how might this impact life that lives in our ocean? How do they take advantage of it? How are they helped or hurt? Whatever, come up with ideas, talk with your neighbors. How does this impact life in the ocean? The fact that internal waves exist. I'll give you about a minute. If you're a fish and you lay your eggs, hypothetically, let's say you're a fish, you've laid in the ocean, not in the freshwater here, and you lay 5,000 eggs, and they're in a clump this big, so tiny eggs. Do you want them all right here? Why? Okay, it's either one really awesome snack for everybody, which means if something discovers this cluster of eggs, they're all dead at once if something eats it, right? Okay, what's a better way for you to make sure that your offspring have a better chance at life? If you spread them out. Now, fish aren't going to, grab their baskets that they weaved out of kelp and go and carry them around and drop them different places, right? Fish don't do that, to my knowledge. So how are they going to spread their eggs around? So maybe they do little bits at a time, or maybe, just maybe, these fish have evolved to lay their eggs at a depth for which they don't have to do anything else. Because if they lay their eggs where a picnicline occurs, and all of a sudden you get internal waves that come in, and over time start to move bits of these eggs away, then all of a sudden our eggs are going to spread themselves out without having to do anything else. This is a huge help for fish that do exactly that. This can move eggs wildly far apart. So this spreads eggs out. Spreads, I'm going to say offspring far and wide. And I lied, it's shorter, just say around. Okay. Beyond that, the other big part that happens is when we get freshwater introduced in runoff and things like that, oftentimes if we're washing off of somewhere where there's been a lot of biological activity, you're going to get new nutrients and things that feed into the ocean, right? If those nutrients happen to sink down or eventually reach that picnic line, we now have these big currents that then carry these nutrients along with those fish eggs and whatever else all around the ocean, around the coastlines. This transports materials, whether it's specific life or the nutrients and ingredients that we need for life. This helps transport it around the ocean and make sure that those resources are spread evenly, roughly evenly. Okay, last little piece. We're not going to write a ton about it, but last class at the hatchery, I had some of you guys doing some crazy stuff with waves. Were you guys able to see it? Okay, there were a couple people who weren't here on Thursday, so we're going to check it out. Leanne, will you take a step and just hold this here? Cool. Thank you. Okay, so right now, I'm going to send a wave toward Leanne. Now, you're going to literally see it propagate over this stream, which means I'm going to make a crest, and you're going to see that crest shoot across. So if you didn't see this last class, there it is. It shoots across, right? It bounces back at me. Are there places in the ocean where there's an enclosed area like this? No? There could be. Can you give me an example of one?
Like two islands right next to each other.
Two islands might do this. So we're in Alaska right now. You might call it Dutch Harbor, and you said the bay. There are definitely places where waves are going to be refracted and come in and get stuck back and forth between each other, right? Okay, so when I send a wave to Leanne, you see it, a crest meets her, and if you haven't noticed it, when this crest gets to her, it flips itself and turns into a trough and heads back to me. So you can see it happening. Now, I can make waves go, but if I do it at just the right frequency, right now, there's something special happening in the middle, like right in front of Taquita. Is there a spot that seems essentially the same height all the time? Now, this is an example of what we call a standing wave. Right there in the middle, where it's essentially the same height, and I just have to get the frequency right here, it's called a node. That node is that part of that water, or that wave, that seems to not move at all. Okay, so we have a node. If we look at a different type of standing wave, the nodes are harder to find. If we slow the frequency down, this wave, I don't see it propagating. It's not moving like from me to Leanne, but it is moving, right? Now, I can't do it without moving my hand, but my height over here is essentially constant, and Leanne's height is constant. These are the nodes of this wave. When we contrast, weird, I don't work with the weird emphasis on it. We'll get it going back the same way, possibly. We'll pull it tight, kill it. Okay, there it is. Okay, when we get back to here, we still have that node in the middle, almost. There it is. And then we have two places where there's very big changes, right? We see large changes in the height over here. If it's a node there, is there a word that we can put about changes like to mean? I'm not even going to ask for it. We have node that stays the same height, and antinodes are the parts that change. Antinode and node. You're good. Cool. All right. So, with that, thank you for doing that, Leanne. That's all I got for you. Okay. So, on a piece of paper, before I head over to the hatchery, here's what we're going to do for like the next 3 minutes. As always, we're going to use a quick bathroom break. I'm cool with that. Somebody in your group, don't care who you guys elect, grab a book out of one of your 3 desks. Cool. Okay. On a piece of paper before we head over there, because this is what I want you working on in the downtime. You might have to check another desk, just a heads up. In the meantime, we're going to call this homework 4.2, which will really be classwork, but you'll have time to do it.
Will you take it?
Yeah, I'm going to take it.
Out of the book?
What's up?
Like out of the book? Like a page?
Yeah, with the big class, I'll probably take it out of your notebook. So do it on a new sheet of paper, page 95, 1 through 3. Okay, depending on how it goes over there, I don't love the idea of having to give a quiz the day that we finished it, but if people aren't working and I have to give a quiz, we'll do a quiz. Cool. I'd rather not, but cool. All right. This is your assignment. You're going to take a book over there. We get